we'll get started. Well, happy Monday. It is week 9, end of February. March is tomorrow, and I know technically spring doesn't start until March 21. Is that equinox? Vernal equinox? Spring equinox? I don't know, whatever it is. Okay. But it feels like spring after we had like that cold week, and it's like the weather's so nice today. It's great. I hope you guys are doing okay. Yeah. And I know, ninth week, a lot of stuff's going on. Just with the quarter, apparently apartment signups, but also, just internationally, it's hard. I think, as hard as it is, I am encouraged kind of by like the global response. I feel like a lot of the nations are kind of coming together to support. So, but yeah, of course our hearts go out to the people of Ukraine. So, all right, we left off on Friday talking about hypothesis tests, doing kind of statistical inference. And here we're going to just kind of revisit a classical statistics approach to comparing proportions. We're going to do a hypothesis test where we compare proportions. I'm going to first take a classical approach. And this is just a silly example that I made up. Don't quote me on any of these numbers because I completely made them up just for the purpose of this example. But I just said, is the proportion of international students different for stats majors and applied math majors? And I have no idea what this is. So I just said, let's get a random sample of 150 students majoring in statistics. And again, this is kind of silly because you could just ask the stats department who's majoring in statistics and you get the whole population and get your answer. Okay, but we're going to pretend we're going to get a random sample of 150 students. We're going to say 75 of them are international. We get a random sample of students majoring in applied math. 64 of them are international. And we're going to ask, does this provide evidence that the proportion of international students is different for stats majors versus applied math majors? And so this is kind of what we would do is this would be a 2-proportion z-test. We could also do a chi-squared test for independence. And if you took AP stats, you probably learned both the 2-proportion z-test and the chi-squared test for independence. But if you took stats 10, at least if I were to teach stats 10, I only get to the 2-proportion z-test. I don't have time to cover the chi-squared test. But we would just kind of look at these 2 proportions and would say p hat, proportion of international students for statistics, it would be 75 out of 150 or 0.5. Proportion of statistics or international students for applied math majors, p hat would be 64 divided by 160 or 0.4. And if we compare 0.5 to 0.4, we say that's a difference of 10 percentage points. 10 percentage points. So we're getting a difference of 10 percentage points in our sample of data. The null hypothesis, at least the way we phrased our question, we said, is there a difference in the proportion of students who are international? And so our null hypothesis would be that there is no difference, that the proportion of students who are international is the same for stats majors as it is for math majors, or applied math majors, I should say. And we would express this as the proportion of international students for stats minus the proportion of international students for math. That difference is 0, that there's no difference between these 2 proportions. And if we do observe a difference in our data, that difference is a result of just kind of random sampling, right? If we sample different people, we might have gotten some different proportions. Okay, the alternative hypothesis is that the difference between proportions is not 0. That if we take this difference between these 2 proportions, we're going to get a value that's not equal to 0. And that's what we have. Okay, if the null hypothesis were true, we're expecting a difference of 0. What we happen to get, we got 0.5 versus 0.4. We got a difference of 10 percentage points. Okay, and the question is that difference of 10 percentage points, is that statistically significant? So the classical approach is to use the central limit theorem. The central limit theorem says, when you look at the sampling distribution of proportion, it's going to be normal. And if you look at the sampling distribution for a difference between proportions, that too is normal. And in our case, if the null hypothesis were true, the null hypothesis says the population proportions have a difference of 0. And if the population proportions have a difference of 0, we would expect our sample proportions also to have a difference of 0. But, we acknowledge that when I take a random sample of stat students, I take a random sample of math students, because it's random, sometimes I get more international students, sometimes I get fewer international students. I might not get a difference exactly 0. Sometimes it's going to be higher, sometimes it's going to be lower. And we're going to say, well, we're expecting it to be around 0, at least centered around 0. Sometimes it's higher, sometimes it's lower. It's going to follow a normal distribution. The mean is 0. And then we have this complicated formula for the standard error. And we just throw that in there. But basically, normal distribution centered at 0, and there's some kind of standard error. We want to figure out the p-value being, what is the probability of getting a difference of 0.1 or something something bigger than 0.1 if kind of the only source of variation is just randomness, right? If the null hypothesis were true and it's coming from this sampling distribution, what's the probability we get 0.1 or something more extreme? Okay, and in this case, because we just want to know if there's a difference between the proportion of international students who are stats majors and the proportion who are math majors, we just want to know a difference. We're interested if that difference is greater than 0. We're also interested if that difference is less than 0. In our data, we happen to get more international students in the stats major than in the math major, but it would also be interesting to us if the opposite were true, if there were more international students that were math majors than there were stats majors or something like that. So here we're going to look at the absolute value. We want to know what's the probability that the absolute value is greater than 0.1. So we do some calculations, we plug all of these things in, we get a z-score of 1.77. You look that up, your p-value ends up being 0.0768. This is kind of the diagram that we get. So again, we're assuming, or if we assume the null hypothesis is true, we expect p hat 1 versus p hat 2 to have a difference of 0. What we got was a difference of 0.1, and we want to know how often does that happen. So 0.1 or greater is around 0.038. Negative 0.1 or more negative has an area of also 0.038. And when you add those two together, you get 0.0768, I guess, 0.0768 if you include the 0.0384. So when you do that, you get a p-value of around 7%, 7 to 8%. If your significance level is 5%, you would say our p-value is greater than alpha, and therefore we do not reject the null hypothesis. Our p-value is not huge, but it's also not so small that we can ignore it, okay? So it says, yeah, even if the proportion of international students and statistics students who are international and applied math students who are international, even if those proportions were the same, when you draw random samples, it's possible that by random chance, you get too many international students in one group and too few in the other group, and you get a difference of 0.1, okay? And that could happen, and that happens with a probability of around 7 to 8%, okay? So not huge, but not small enough for us to dismiss it. So because of that, we're going to say this difference of 0.1, we can't, it's not big enough for us to conclude that there is a difference in the populations. On the other hand, we cannot say that it proves that there's no difference, okay? We just have to say it doesn't tell us that there is a difference between the population proportions. Okay. All of our calculations were based on the central limit theorem, right? There was kind of this assumption back here that this sampling distribution follows a normal distribution. Okay, and that's what the central limit theorem allows us to do. And because of that, we can draw the normal distribution, and that's how we do our test. In order to apply the central limit theorem, there's a few conditions. One of them is that your samples have to be large enough. And depending on what textbook you use, large enough could be a few different things. A lot of times the rule we use is we say you need to have at least 10 yes and 10 no in both samples. So we need to have at least 10 students who are international and 10 students who are international. And that condition was met, and so we can use the central limit theorem. But if you have a sample where it's not big enough, it doesn't meet this criteria, then you can't use the central limit theorem. You can't assume that it follows a normal distribution. And if you do use the normal distribution, it could give you the wrong p-value. It could end up leading to the wrong conclusion. So, what do we do in a situation like that? Because we might be in a situation where we don't have a big enough sample. So one choice is to do the randomization test. Okay, and so that's what we're going to introduce here. Okay, before I go on, let me go ahead and give you your first view quiz answer, which is the letter D. D as in dog. D as in dog is your first view quiz answer. Okay, I'm going to play a video. Okay, hang on a second. All right, so I have to pause the video. This is from Mythbusters. I don't know if you guys ever watched Mythbusters. It was a great show. It was on the air for a while. I don't know how old this episode was. Okay, oh man. Originally aired 2005, so that's what, 17 years ago or something? Okay, I actually had to purchase this episode from YouTube, and I have to pause the recording of the video because one time I let the video record and this thing played and then I got hit with a copyright strike. So I'm going to pause it. If you're watching online, there's a jump cut, and we'll pick up right after the video has stopped playing. You can probably search online for Mythbusters is yawning contagious, and you might be able to find somebody else who uploaded the video to some site somewhere, but it's not going to be me. All right, so I'm going to go ahead and pause this. We'll see you in a bit. Okay, I think, oh wait, hang on. Is this working? All right. Okay, so we watched the video. If you're watching online, let me just give you a quick recap. So on the Mythbusters TV show, they wanted to see if yawning was contagious, and the way they tested this was they set up this station. They selected 50 people to participate, and each participant was told to just sit in the room, and they were monitored for several minutes. But before they enter the room, some of the people saw a person yawn right before they entered the room. We called this the seed yawn group. And then other people didn't see the person yawn. And the question was, if the person who sees the yawn, are they more likely to yawn when they're sitting versus the people who didn't see the yawn, to see if yawning is contagious. And so they were kind of recording that. And in the video, they said every third person was control, and then they kind of gave numbers. They said 29% versus 25%. So we backwards solved to figure out what these numbers were. And so I said, well, if 1/3, so 1/3 of 50 is around 16, 17. So they said in the control group, 25% yawn. So that's got to be 4 out of 16. And in the seed yawn group, they said 29%. So that's going to be 10 out of 34 people yawn. So we're going to have a total of 50 people. 10 out of 34 yawned in the seed yawn group. 4 out of 16 yawned in the control group. Now, one thing to note is the people that were selected it's not a random selection, okay? But the treatments were randomly assigned. Technically, they were systematically assigned in that they said every third person is in the control group. But if you think about, if you imagine this line of 50 people coming in, the order of people in that line is kind of random. So on another day, those 50 people could be in a different order, and then different people would have been in the control group and different people would have been in the CDON group, okay? And so at the end of the video, they came to the conclusion, well, they said 29% versus 25%, they said something along the lines of, well, the difference isn't dramatic, but because their sample size was so huge, this seems to confirm the idea that yawning is contagious, because 29% is greater than 25%. Seeing the CDON makes you more likely to yawn than in the control group, okay? And then the narrator says, there's little doubt it does seem to be contagious. And then they showed the confirmed stamp there, okay? So what I want to do is I want to test this if this is actually, if that's the case, all right? So we're just a bit of notation. We're going to set up a hypothesis test. We're going to say, probability C, this is going to be the probability that someone yawns if they see someone else yawn, if they're in the CDON group, okay? And then we have probability control. This is the probability someone yawns if they don't see anybody else yawn. That's going to be the control group. And the null hypothesis is that there's no difference. Probability of yawning in the seed group is the same as the probability of yawning in the control group. The difference between these things is 0. Yawning is not contagious. And the alternative is that yawning is contagious, that if you see someone yawn, you're going to be more likely to yawn than if you don't see someone yawn. So we're going to say the probability of the seed yawn, the probability of yawning for the seed group is greater than the probability of yawning in the control group, or that the difference between them is greater than 0. And what we observed was something greater than 0. We got 29% versus 25%. We got a difference of around 4.4%, 0.044. Okay, 10 out of 34 minus 4 out of 16 gives us a difference of 0.044. Again, we're expecting a difference of 0. We got a difference of 0.044. And the question is that difference statistically significant? Okay, is this all right? The setup here? Okay, so what we want to do is we want to say, well, what sampling distribution do we have if the null hypothesis were true? And again, our samples aren't big enough for us to use the central limit theorem, okay? So the way we're going to do this is we're going to just say, well, let's think about this for a moment. If the null hypothesis were true, we're going to say whether a person yawns or not has nothing to do with whether they saw the seed yawn or they didn't, right? They're just going to yawn. Some people are going to yawn and some people aren't going to yawn, okay? So we can, it's a little bit of a funny thing to think, or to use the word destiny in this way, but we're going to say for 14 of these people, it was their destiny to yawn, okay? They were going to yawn anyway, right? And out of the 50 people, 14 of them were going to yawn no matter what. 36 of them were not going to yawn. And the fact that in one group, 29% ended up yawning, and in the other group, only 25% ended up yawning, that's just a result of the random assignment and had nothing to do with whether there was a seed yawn or not, and they were in the control group or not, okay? And we're going to, under the null hypothesis, we're going to just say that randomness alone could produce this difference in proportions of, 0.044. Okay, so the p-value is, again, the probability of observing our difference or something more unusual if the null hypothesis were true. If the null hypothesis were true, we would expect the proportion of yawners to be the same for both groups, so we would expect to see a difference of 0, but we got a difference of 0.044. And so the p-value here is if the two populations have the same proportion of yawners, what's the probability that random assignment could produce samples of data where the difference is 4.4% or something more unusual? So what we're going to do is we are going to simulate the sampling distribution when the null hypothesis is true. Okay, we're going to use a randomization test, which doesn't require the central limit theorem, doesn't make any kind of assumptions about normality or anything like that. All we're going to do is we're going to say random assignment is the source of variation, or the source of kind of randomness between sample proportions. So what we're going to do is I'm going to have 50 people, and of those 50 people, I'm going to say 14 of them are going to be yawners, okay? 14 will yawn, The other 36 will not yawn. And then I'm going to shuffle that up. I'm going to just shuffle those up. And then I'm going to just deal 34 people into group A and 16 people into group B to kind of make parallel groups to what I did in the experiment. In the experiment, we had 34 in the treatment group, 16 in the control group. Okay, so here I'm going to shuffle up these 50 people, just randomly put 34 of them into group A, 16 into group B. When I put the people into group A versus group B, the only reason why group A would be different from group B is because of the random assignment. We've done nothing else to the groups. Okay, all we've done is we've taken these 50 people and we just shuffled them up, put some into group A and some into group B, and then we're going to say if we do see a difference between group A versus group B, we know that difference is just because of the random assignment. We've done nothing else to these groups. Okay, so if there is a difference, that kind of difference is a result of just randomness alone. And what we're going to do is we want to know, okay, well, what kind of difference can we end up getting between group A and group B? We're expecting differences of 0. Maybe we'll get differences of 4.4%. Maybe we'll get bigger differences. Who knows? That's what we want to know. Okay? And so what we'll do with the randomization test is we're going to repeat this randomization process a lot of times. And every time we do this, we're going to record the difference between group A and group B. Okay? And yeah, for every randomization, we record that difference. We're going to keep track of them all. And we'll see what kind of differences can result from just the randomization process. Again, we're doing nothing else other than shuffling them up and just saying, I'm putting 34 into group A and 16 into group B. And we're doing those numbers because those are the numbers that we used in the experiment. Okay? And we want to know, okay, is this difference that we got in the actual data, the actual observed data produced a difference of 0.044, we want to know, is that difference of 0.044 unusual or not? And so if it turns out, so maybe we do this a whole bunch of times, and if it turns out that it's very unlikely to get a difference of 0.044 from randomization, then the fact that we got 0.044 would suggest that our null hypothesis is wrong, and that the reason why we got 0.044 is something other than randomization. Okay, but another possibility is that 0.044 is a common occurrence from randomizing. So we do the randomization process, maybe we get 0.044 quite a bit, and that this result is not a strange thing. Then we would just say, well, maybe we got 0.044 from just randomness. Okay. And so we're going to do our randomization test. We're going to see what kind of results we get. Okay, now, before I go on, one important thing is that there is an assumption we're making here. Okay, we're not making the central limit theorem distribution assumptions, but the assumption here is exchangeability. Okay, exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely, and any permutation of the data is exchangeable with any other permutation of the data. All right, so it's a bit of a mouthful. What exactly does that mean? It basically means, well, the exchangeability thing is going to hold true when you have an experiment where random assignment was used. Okay, again, if this experiment were to have been done in a parallel universe or just on another day, the 50 people that lined up, they could have ended up in a different order, and different people would have ended up in the control group, and different people would have ended up in the treatment group. Okay, and we're going to say that any kind of combination of who's in the control group and who's in the treatment group, any one of those combinations are equally likely and equally valid. Okay, and I would agree that would be true. That under the null hypothesis that this concept of exchangeability exists. Okay, if you are not doing random assignment and you're doing some kind of observational study, okay, then exchangeability does not hold true. Okay, so for example, if you wanted to know, is there a relationship between, say, people who exercise and whether they have high blood pressure or not? Okay. We can't just assume that on another day, these people it's just equally likely that these other people are now the exercise group and these people are not the exercise group, right? There's whether somebody chooses to exercise or not is probably related to a bunch of other lifestyle choices and other kinds of things. And so we can't just assume that every combination is equally likely, okay? Whereas when it's random assignment, who ended up in this group and who ended up in that group was just a random thing. We could say any other kind of switch and every kind of assignment of these things is equally valid. But if it's something like, a trait or a decision that somebody's making and it's an observational thing, we can't just swap the conditions and variables. So we can't do exchangeability there, okay? Okay, so anyway, exchangeability applies in this scenario, and this is how we're going to set up our data. So here I'm going to set up my vector of who yawns and who doesn't yawn. This is a vector of length 50, and I've created this by repeating just true and false values. So the first 34 people, where I repeat true 10 times and I repeat false 24 times, that's going to represent kind of my treatment group, the 34 people who are in the seed yawn group. And then the last 16 values, where I have true repeated 4 times and false repeated 12 times, that's going to represent the 16 people in my control group, okay? So here I have a vector of length 50. The first 34 will be my treatment group. The last 16 will be my control group. I've got 10 out of 34 in the treatment group that yawn, 4 out of 16 in the control group that yawn. And so when I calculate the proportion that yawned for the treatment group, I get 10 out of 34, or a proportion of 0.294. And for the control group, I get 4 out of 16, I get a proportion of 0.25, okay? And so our observed difference for our actual data is going to be 0.294 versus 0.25. I get a difference of 0.044, okay? So this is just setting up the data, and I want to make sure we're all okay with kind of the use of repeat here to kind of create this logical vector of trues and falses. Okay, so the way we're going to do the shuffling, because again, we're going to just say, I'm going to take these 50 people, I'm going to shuffle them up, put some into group A and some into group B. We're going to just use the word sample, right? So the function sample just takes a vector and just shuffles them up, okay? Sampling without replacement, okay? And basically, every time I call a shuffle on yawning, the output vector is still going to be length 50, and it's always going to have 14 true values and 36 false values, but the order will be randomized each time. So, so here, just for one example, I sample these, I shuffle them up, and I'm going to put the first 34 into group A and the remaining 16 into group B, right? And the only reason why group A would be different from group B is from the shuffling process only. I haven't done anything else to these groups. And I say, what's the mean of group A? I get 0.294. What's the mean of group B? I get 0.25. So coincidentally, I got the same results that I got in my observed data. So that's just kind of a coincidence of this thing. I get a random difference of 0.044. So just by coincidence, I get the same results that I had from the original thing, but we want to know, okay, is this an unusual thing? Is this just a weird fluke that just happened this one time? So we'll just try it again, okay? So here I do set seed 5, and I do this again. Oh, you know what? Let me give you another view quiz answer. This is your second view quiz answer, and it's the letter E. E as in elephant. E as in elephant. Okay, so here I shuffle up those 50 people. After I shuffle them up, again, we have a total of 14 people who are going to yawn. I shuffle them up. I put people into group A, people into group B, and I say, well, okay, what's the proportion in group A that yawned? I get 0.235. What's the proportion in group B that yawned? 0.375. So if I have 16 people in group B, I guess this is going to be like 6 out of 16, which means I had to have 8 out of 34 in the other group or something. Okay, whatever it is. Okay, so this is what we get when we calculate the difference between these two proportions. Group A actually has a lower proportion, 0.235 versus group B, and we have a difference of negative 0.1397, so around difference of negative 14 percentage points between these two group proportions. Okay, and so that happened just from randomness. And so what we want to know is, look, okay, what if I do this a whole bunch of times? And so this is going to be kind of my primary randomization test. I do set seed 1. I'm going to do this, repeat this 10,000 times. I'm going to have 10,000 differences that I'm going to calculate. And each iteration, so I'm going to do for I and sequence along differences, every time I'm going to shuffle that vector yawning, and then I'm going to just put the first 34 into group A. I'm going to put the remaining 16 into group B, and then we're going to calculate the difference between the proportion in group A and the proportion in group B, and we're going to keep track of all of these differences. Okay. I've set the seed for reproducibility. If you set a seed, make sure you do it outside the loop. Don't ever set the seed inside the loop, because you'll get the same results every single time inside the loop. So don't set the seed inside the loop. Okay. So here, again, shuffling it 10,000 different times, every single time, 34 into group A, 16 in group B, we're going to calculate the difference between these two proportions. Okay, and if we look at the mean, we get something close to 0, which is what we expected under the null hypothesis. We get the median is actually 0.044, okay? The smallest value I got was negative 0.599, okay? So one time I got a difference of proportions of negative 0.59, and one time I got a difference of proportions of 0.411 in the opposite direction. But let's just take a look. Okay, so our question was, how often do we get our data or something more extreme if the null hypothesis were true? So this is what would happen if the null hypothesis were true. If the null hypothesis were true, who ends up in group A and who ends up in group B is a result of just randomization alone. And that's what we've done. We've simulated what would happen from randomization alone. We've randomized people, put some in group A and some in group B. And we say, okay, well, how often do we get a difference of 0.044, which is our observed difference? Okay, so how often did this happen? So we're going to ask, okay, differences greater than or equal to our observed difference. This is going to be a logical vector. And what's the proportion where this is true? This happens 50% of the time, okay, around 51% of the time. So by random chance, I would get a difference of 0.044 or something bigger around 50% of the time. Okay, so Mythbusters came to the conclusion that this difference of 0.044, I think they said something along the lines of, well, it's not dramatic, but because our data is so big or sample is so big, it's I'd say it's confirmed, or it's pretty conclusive, or whatever they said. Okay, and it turns out, well, no, you could have just gotten this with a coin flip, right? That you could have gotten a difference of 0.044 just kind of from randomness, if not because the seed yawn did anything actually significant or not. And in fact, okay, so all right, I'll just read this slide. Okay. So it says, the randomization process has a high probability of producing the data we observed in the Mythbusters experiment. So we have no reason to believe that the data we observed was caused by something other than randomness, and we would not reject the null hypothesis. The data does not provide reason to believe that getting a seed yawn makes a person more likely to yawn. On the other hand, we can't say that yawning is not contagious. Our data simply does not provide enough evidence that it is contagious. It's possible that a seed yawn increases the probability of a yawn, but maybe we didn't collect enough data. Or it's also possible that a seed yawn does increase the probability of a yawn, but just maybe on that day when they did the experiment, we didn't get people who yawned, okay? That's also possible. We don't really know. But right now, it's not going to convince us that the seed yawn is actually contagious. What if we had a two-sided alternative? What if we said, does seeing someone yawn have any effect, positive or negative, on a person yawning? Okay, and that would be that would have a two-sided alternative. We'd be interested in the absolute value being greater than 0.044. Okay, and when you do this, we get a p-value of 1, and p-value of 1. 100% probability. That seems strange. We almost never get p-values of 1. So this feels weird, but really, actually, the p-value is 1. And let me just kind of show you what's going on. So in our data, we had 50 people total. 14 people yawned and 36 did not. And so what we got is, if I go through these, we have a split where 10 in group A and 4 out of 16 in group B. Okay, and so 10 out of 34 is that, 4 out of 16 is that. The difference between 10 out of 34 and 4 out of 16 is 0.044. Okay, another possibility is I could have gotten 9 versus 5, right? We have 15 people total, so I could put 9 in group A and 5 in group B. 9 out of 34 is this proportion, 5 out of 16 is this proportion. The difference between 934 and 516 is a difference of negative 0.0477, which is actually a bigger difference than 0.044 as far as absolute values go. Okay, what are some other possibilities? I could have gone 8 and 6 for a total of 14. And if you calculate the difference between 8 in group A and 6 in group B, you would get a difference of negative 0.1397. Which I think is what we got in one of our examples. You could keep in the other direction. You could say, well, if I didn't get 10 and 4, maybe I got 11 and 3. The difference between 11 in group A and 3 in group B is a difference of 0.136. This difference is 0.136. Okay, and more extreme would be 12 in group A and 2 in group B, and that would be a difference of 0.227. Okay, so and if you look at any other kind of possibilities, I guess another one would be 7 and 7. Okay, 7 out of 34 and 7 out of 16 for a total of 14 people. Okay, that would give us a difference of negative 0.23. Okay, so if you look at all of these differences, 0.044 is actually the smallest possible difference we can get. Okay, you cannot get a smaller possible difference, because if you flip and change any of these numbers, you might get negative 0.047, you might get negative 0.139, you might get negative 0.23, or positive 0.136, or positive 0.227. The only way you could get something smaller than 0.044 is if you had like 9.5 and 4.5. Okay, so instead of 10 and 4, if you said, well, I had 9.5 versus 4.5 people, sure, that would give you something closer to 0. But you cannot have 9.5 yawners in one group and 4.5 people who yawn in the other group. You're either going to have 9 and 5, or 10 and 4, or something like that. You can't have half a person. And so Mythbusters is like proud of their 4 percentage point difference, 0.044, but it's actually literally impossible to get anything smaller than a 4 percentage point difference between these two groups. So, as far as I'm concerned, yeah, this is not very convincing at all. A difference of 4 percentage points is not significant. So yeah, that's what. Unfortunately, if you search "is yawning contagious," it's going to come back and say yes, and they're going to look at from the Mythbusters experiment and something like that. But yeah, I mean, I don't know. Maybe there's more evidence otherwise, but that's where we've left off. Okay, that's all I've got for today regarding randomization tests. Let me give you your last view quiz answer, which is the letter C. C as in cat. C as in cat is our last view quiz answer for today. Okay, we'll end here. Have a good rest of your day, and we will see you on Wednesday.